Hello, I'm Denise, one of the presenters of the Enlightenment Project. We are pleased that you have decided to join us on this extraordinary journey through enlightenment. In today's video, we will explore the laws of motion and vibrational frequencies. Did you know that vibrational frequencies are typically measured in Hz Hz, where 1 Hz is equal to 1 oscillation per second? For example, if a guitar string vibrates back and forth 440 times in 1 second, its frequency is said to be 440 Hz, which corresponds to the musical note A above middle C. Did you know that the phrase, to be on the same vibrational wavelength, is often used metaphorically to describe a situation where two people or entities are in harmony or agreement with each other? It implies that they share similar thoughts, feelings, or attitudes, and are able to communicate or connect effectively. This concept is derived from the idea of resonance in physics, where two systems can oscillate at the same frequency, leading to an amplification of the vibration. In the context of molecules and atoms, vibrational frequencies are associated with the movements of atoms within a molecule. These vibrations can be stretching, bending, or twisting motions. Did you know that the foundation of classical mechanics is built upon several key principles and laws that describe the motion of objects and the forces acting upon them? Well, we invite you to sit back, relax and vibe with us on this fascinating journey through enlightenment.
What if I told you that everything you touch, see, and even you yourself are constantly in motion, even when seemingly still? This might seem like a riddle, but it's the reality of our universe. Everything around us is made up of tiny particles, so minuscule that they are invisible to the naked eye. Each of these microscopic particles is in a constant state of vibration, always moving, always dancing. This perpetual dance isn't random. These particles move in harmony, their motion choreographed by the laws of physics. The way they vibrate, the frequency of their movement, determines the motion of the objects they form. Whether it's a feather falling from the sky, a guitar string humming a melody, or a planet circling a star, these movements are the collective ballet of countless particles vibrating in unison. In essence, stillness is an illusion, and motion is the fundamental nature of the universe. Have you ever wondered what causes an object to move or change its state of motion? It's all about vibrations. You see, everything in the universe is made up of tiny particles that are constantly in motion, vibrating at specific frequencies. Consider for a moment a guitar string. When you pluck a string, it vibrates, producing a sound. The frequency and amplitude of these vibrations determine the pitch and volume of the sound we hear. Similarly, in the realm of classical mechanics, the motion of an object is a result of the collective vibrations of its constituent particles. So, what happens when an external force comes into play? Just as strumming a guitar string changes its vibrational state, altering the sound it produces, applying a force to an object changes the vibrational state of its particles. This, in turn, leads to a change in the object's motion. Now you might be wondering how this vibrational perspective ties into the classical laws of motion, like those put forth by Sir Isaac Newton. Well, it's quite fascinating. The forces acting on an object are, in fact, manifestations of the interactions between these vibrating particles. For instance, the force of gravity can be seen as the result of the attraction between the vibrating particles of two masses. This perspective is particularly relevant in the realm of quantum mechanics, where the wave-like nature of particles is more pronounced. However, it also provides a useful conceptual framework for understanding classical motion, especially in systems where vibrational and wave-like phenomena play a significant role, such as the behavior of molecules and solids. At the heart of it all, classical mechanics is a well-established and highly successful framework for understanding the physical world. It's applicable to a wide range of scales, from everyday objects to planetary motions, and forms the basis for many of our scientific and technological advancements. So, just like strumming a guitar string, forces can change the tune of matter's motion. How can we connect these vibrations to the laws that govern the motion of objects? Let's dive into Newton's laws of motion and see how they can be interpreted from a vibrational perspective. Newton's first law, also known as the law of inertia, states that an object at rest stays at rest, and an object in motion stays in motion, unless acted upon by an external force. But when we look at this through our vibrational lens, we see that what keeps the object in its state, whether at rest or in motion, is the consistent vibration of its particles. Now let's look at Newton's second law. It tells us that the force acting on an object is equal to the mass of that object multiplied by its acceleration. From the vibrational perspective, when an external force is applied to an object, it alters the vibrational state of its particles. This change in vibration leads to a change in motion, which we recognize as acceleration. Finally, Newton's third law, commonly known as the action-reaction law, states that for every action there is an equal and opposite reaction. In terms of vibrations, this means that when the particles of one object interact with those of another, their vibrations affect each other equally, just like two tuning forks that start to vibrate in unison when one is struck. So, forces, according to this perspective, are manifestations of the interactions between vibrating particles. For instance, the force of gravity can be seen as the result of the attraction between the vibrating particles of two masses. This perspective is not only relevant in the realm of quantum mechanics, but it also provides a useful conceptual framework for understanding classical motion, especially in systems where vibrational and wave-like phenomena play a significant role, such as the behavior of molecules and solids. So, Newton's laws aren't just rules for motion, they're also a symphony of vibrations. Let's continue to explore how these vibrations play out in the quantum realm, and how they connect us, humans, to the laws of motion and the universe itself. But what happens when we delve into the tiny, mysterious world of quantum mechanics? This is where the vibrational perspective becomes particularly relevant. In the quantum world, particles don't behave like tiny billiard balls, but more like waves on a pond. They vibrate, they resonate, and they interfere with each other. And these behaviors are not just metaphors, they are actual, observable phenomena. Think about the double-slit experiment, a classic demonstration of quantum weirdness. When we shoot particles like electrons through two slits, we don't just get two bands of particles on the other side as you'd expect if they were just tiny balls. Instead, we get an interference pattern, like waves on a pond. This tells us that the particles are not just traveling in straight lines, but are spreading out and interfering with each other like waves. And it doesn't stop there. Even when we shoot one electron at a time, we still get the same interference pattern. This is because each electron doesn't just take one path through the slits, but all possible paths at once. It's as if each electron is a tiny vibrating string, exploring all possible notes it can play. This wave-like behavior is not just a quirk of electrons, but a fundamental aspect of all particles. In quantum mechanics, particles are described by wave functions, mathematical entities that give the probabilities of finding the particles in different states. These wave functions vibrate and resonate, and their interactions give rise to the phenomena we observe. So, in the quantum realm, the vibrational perspective is not just a convenient analogy, but a fundamental aspect of reality. The motion of particles is not just about their positions and velocities, but about their vibrational states and the way they interact. And these quantum vibrations are not confined to the microscopic world. They can have macroscopic effects too. For instance, the colors of objects, the stability of matter, and even the workings of our brains can all be traced back to quantum vibrations. Quantum mechanics takes our symphony of vibrations and turns it into a full-blown orchestra. So, how does all this talk of vibrations and motion connect to you and me? Well, let's delve into that. Just as the universe and everything in it, humans and indeed all living beings are made up of countless tiny particles. These particles are in a constant state of vibration, humming along at their specific frequencies. You could think of this as our own personal symphony, playing a unique composition that is ours and ours alone. Every action we take, every interaction we have, is governed by the same laws of motion and vibration that we've been discussing. When we move, our particles vibrate at different frequencies, leading to a change in our motion. This is the same principle that applies when an external force is applied to an object, causing a change in the vibrational state of its particles. Take, for instance, the simple act of walking. With every step, there's a complex interplay of forces and vibrations. The force exerted by our muscles on our bones sets them in motion. This motion is the result of the collective vibrations of the particles that make up our muscles and bones. And it's not just our actions. Our interactions with others are also a dance of vibrations and forces. When we touch something or someone, the particles of our skin vibrate against the particles of the object or person. This interaction alters the vibration of our particles and theirs, leading to a change in both our states. This understanding of ourselves as vibrating entities doesn't just apply on a physical level. Our thoughts, our emotions, our very consciousness may also be understood as the result of complex vibrational patterns within our brain. So, when we say that we are all connected, it's not just a metaphor. On a fundamental level, we are all part of this vast, vibrating universe, each of us playing our unique part in the grand symphony of existence. So, in a sense, we are all part of the grand orchestra of the universe, playing our unique tunes. So, we've journeyed from the macroscopic world of classical mechanics to the microscopic world of quantum mechanics, all through the lens of vibrations. We've seen how every piece of matter, from the strings of a guitar to the molecules in our bodies, is made up of tiny particles vibrating at different frequencies. These vibrations govern how things move and interact, providing a new perspective on Newton's laws of motion. We've also delved into the quantum realm, where the wave-like nature of particles becomes more pronounced, and where classical mechanics gives way to quantum mechanics and special relativity. But perhaps most importantly, we've explored how all of this is relevant to us as humans. We are, after all, part of this vibrational symphony. The universe is a symphony of vibrations, and you're a part of it. So keep exploring, keep questioning, and remember to subscribe, like, and follow our channel for more enlightening content.